So with chapter 12, we're going to talk about chemical bonds. At this point, we've already talked about the periodic table and we've talked about the structure of atoms. What holds atoms together are chemical bonds. And so that's what we're going to talk about in this. We're going to talk about the bond energy as the strength required to break a chemical bond. We could talk about that as being potential energy. And we're going to talk about two basic kinds. There are more kinds of chemical bonds. We're going to talk about generally ionic bonds and covalent bonds. This is a crash course video that's listed on the Moodle site, so it might be interesting. It does go into a lot of information, so either watch it as an intro or as a recap. It's got a lot of information in it. So the first kind of bonding that we're going to talk about is ionic bonding. And so we have talked about this before in that ionic bonds happen between things from the left-hand side of the step, which are metals, and the things from the right-hand side of the step, which are non-metals. So building on what we know about the periodic table, things over here, these metals like to give electrons. And over here, these non-metals like to get electrons, generally. So over here, these metals giving up electrons tend to form positive ions, and these non-metals tend to get electrons and become negative ions. So these ones would become cations because they are positive, and these would become anions because they are negative. And so this is just illustrating the classic between sodium and chlorine, knowing how many valence electrons they have, and we can see that on the periodic table as either the common ion formed or which family or group they're in. The other thing we could take a look at as examples of ionic bonds, so salt would be a good one, right? Salt, NaCl, or any metal and nonmetal is technically a salt, or any acid, so anything with the hydrogen out front. So hydrochloric acid is also an ionic bond, so acids are also ionic compounds. Let's take a little bit of a closer look around about these. So they occur when one element donates an electron or the electrons are transferred from one atom to another. They occur between different types of atoms, so metals and nonmetals, like I had summarized. The metals donate the electron, becoming positively charged, which are cations, and the nonmetal accepts the electron, becoming negatively charged, or the anion. It's a relatively strong bond, but it's not strong enough to overcome the wily ways of water. And so water can take an ionic substance and break it apart into the ions that make it up. And in this, so that idea here, in salt would float around as sodium ions and chlorine ions in a water solution. And so this is the reason why ionic solutions can conduct electricity. On the Moodle site, you'll see this summary of ionic bonds, and right below it, you'll also see another video that we use later in the course, but just as a little bit of a demo in class, it would show you the demo of why salt water can conduct electricity because it's an ionic solution, whereas we take a look at sugar, which is a covalent compound, which we're about to see on the next side of the page here, it does not conduct electricity. And so that demo, or if I can do it in class for you, that's great, really illustrating that because the compound comes apart into the ions, it allows electricity to be conducted through the solution, whereas a sugar water solution does not conduct electricity because it is not coming apart into its ionic components. So the flip side of the page, we've done a little bit on ionic bonding. Covalent bonding would happen between two non-metals. So I like coming up with examples of these ones because I find that they are generally useful. So anything from beyond the step, so maybe carbon dioxide, maybe oxygen gas. These are two examples of covalently bonded compounds. So they're both from beyond the step over here, these non-metals. They occur when the electrons are shared. And again, to satisfy the duet or octet rules or complete the valence shell of electrons, that's the solution. So ionic bonds is giving and getting, where covalent bonds is sharing electrons. They're relatively strong, again, and they occur between very similar or identical types of atoms. So generally the nonmetals. There's a summary of it here, just a quick one. Covalent bonds can be subdivided into two different kinds of sharing of electrons. So these two different kinds of sharing of electrons, right? So they're all sharing of electrons, but they can be shared equally or they can be shared unequally. So let's start out with the equal sharing. So the equal sharing would be between identical compounds. And of my example, that oxygen is that example. So all the diatomic molecules, if you remember the Hofbrinkels, they are all diatomic gases. And because it's two identical atoms, they share the electrons equally. If we take a look at the opposite of this, or different than this unequal sharing, it happens because of the greediness that electrons or that atoms have, or their hunger for the shared electron. It basically, I talk about it as its level of greediness. Right? It results in an unequal sharing because one of the atoms has the electrons around it more of the time. It ends up being more negatively charged, and as a result, the other one becomes more positively charged. The classic example of this is water. Water is from beyond the step where it bonds with a covalent bond, but because oxygen is so much greedier for the electrons than hydrogen, if we take a look at the water molecule, you end up with the electrons around the oxygen for more of the time, which results in a negatively charged region and a positively charged region. That polarity is really important when we talk about water. And so there's a lot of compounds that come together in this way. This hydrogen fluoride or hydrofluoric acid would be an example of this. And because it's got this unequal sharing, you end up with this bond polarity. And so you end up with this negative region and this positive region. The textbook likes this little sigma notation. I tend to just put negative and positive. Same idea here. There is a little bit of a bonding song. It's really terrible. It's this guy dressed up like an atom and dancing around, illustrating kind of how you can turn these into sort of the way people react. Anyway, yeah, it's time well wasted. You'll also find that on the Moodle site. So this next little bit, as far as ratings go, if we talk about the greediness, right? The nature of the different atoms, we can take a look at that unequal sharing. Over here on the periodic table, we have very, very greedy atoms, or very, very greedy elements. Over here, they're very not greedy. So if we compare the relative strength of that hold that atoms have on electrons, we can see when we end up with a polar bond or a non-polar bond. And so again, we have that idea, the step running down here, roughly. And so generally the trend for electronegativity going across a row, it increases. And going down the group, it decreases. I like seeing like this is the biggest and this is the smallest. So it's more of like an across the way this way, it increases, right? You'll find a slight increase this way and a big increase that way, where this fluorine is the top dog here. Okay, so let's take a look at this. So when an atom has that higher electronegativity, it's more hungry for that shared electron and it holds that electron closer to itself. So the highest electronegativity here would be fluorine. And it has a relative rating. There's no units on these ratings of 4.0. That's just pulled from the document up above. Down here it says which element has the lowest electronegativity on this periodic table, and that would be francium. And its rating is a 0.7 hold. And I don't know the units, or this is just a relative measure. So if we were to compare these, the bigger change between them would be uh, uh, a polar, or sorry, the bigger change between them would mean an ionic bond. The one's so givey and the other one's so getty that you actually make ions that come together. So that would be, like the first kind of bonding that we talked about. In between, so that mid-range of a difference, it's not enough to classify it as ionic, but it does end up with this unequal sharing, this polar covalent bonding. Or if there's very little of a difference between them, that would be a pure covalent, or just a covalent bond between them. And so this scale is pulled from a different resource than your textbook. Your textbook doesn't actually quantify these ranges. And in the textbook questions, if you do all of the questions, not just the ones that I've assigned, you'll actually notice there are some slight variations in these numbers, and so I would correct these numbers to that, but I've also tried to be careful not to assign you questions that really kind of poke some holes. There's lots of exceptions to these bonding rules, and it sometimes depends on the state that the compound is in, and so we'll just talk about these as you know relative measurements. And so pure covalent, this would be equal. An example of that would be the diatomics, right? Or any of the hydrocarbons. So anything that has just carbons and hydrogens in them. Polar covalent, it's enough of a difference that it results in a polarity. So water would be a classic example there. And then ionic, not even in the covalent nature, there's enough of a pull that to have sodium give up its electron and donate it to that very getty or greedy chlorine. And so kind of quantifying these ones, if we take a look at these as we go through, we're going to try and make some sense of it. I find that this is a little bit awkward. In a perfect world, I'd have this right up beside me. And so you'll find the relative ratings are in your formula sheets. And I can't project that in the video here, but I'll just take a look at these ratings. And so in these ones, if I take a look at these bonds, we want to figure out which ones are most polar and which ones are least polar. And so I have to look at the relative ratings. And so I'm pulling these numbers from that given piece of information here. I don't just know these, right? So that the relative change in here would be 1.0. So nitrogen has a rating of 3, fluorine has a rating of 4. So the relative difference would be 1. Oxygen has a rating of 3.5, if I could find it. And again, fluorine was the 4.0, so that gives me a relative rating of 0.5. If I take a look at carbon, again from that document, it had a rating of 2.5 on the electronegativity scale, and fluorine again, 4.0. So a relative difference of 1.5 on that. And so if I were to arrange these from most polar to least polar, I'm going to switch color here, I would say that this one would be number 1. It's the biggest number. This would be number 2, and then this guy would be number 3, just arranging them in order. This one's the least polar. I guess yeah, we didn't go past the 1.7, so we're good. Okay, so if we do another one like this, and again, I'll just pull them from the periodic table. Chlorine and chlorine, there's no difference between those. That would not be polar at all. So it's going to get to be the least, right? So it's pure covalent, not polar covalent. Boron would have a rating of 2.0, where chlorine has that 3.0, so it gives me a relative difference of 1. Whereas sulfur on the table is 2.5 and chlorine is 3.0. And so a relative rating of 0.5 on that. So again, if I switched colors and kind of rank these ones from most polar to least polar, this one that is completely non-polar would be number 3. And again, with this one, I'd go, you get top spot, you get second, and the third ranking there. The next one, these are kind of tedious to do. They're not difficult, but it does take kind of having that reference sheet. Thank goodness we don't have to memorize all this. So I'm pulling these numbers from that reference page. I'd have a 2.3 rating on that. On carbon and oxygen, I'd have a 2.5 and a 3.5. So I'd have a 1 rating on that one. Silicon, be really nice if there was a little more space here, sorry. A 1.8 rating and a 3.5 rating, so a 1.7 difference. And then nitrogen, oxygen would be a 3.0 and a 3.5, giving me a relative difference of 0.5. So now we have to make sense of these numbers, and that's where having that reference page that was added in, not in your textbook, gives me a chance to kind of rank these. So we're looking for which of the bonds would be the most polar without being considered ionic. And so this 2.31 is ionic, so that's going to rule it out. So that's why I wouldn't pick that as my answer here, because it's so different that it's actually, one gets and one gives as opposed to sharing. So that would give my silicon and oxygen the next level spot, right? At that 1.7, it's just on the cusp of being considered ionic, but it would be considered polar covalent with that unequal sharing. Continuing on with these in that bond polarity or dipole moments, it gets represented with this sigma number. So we've already talked about this dipole moment or that relative charge on these. This was my example here between the hydrogen and the fluorine. So the fluorine, being really greedy, gets to take the electron more than the hydrogen, resulting in this unequal sharing or this molecular polarity or bond polarity. Here's the example of H2O or water. And if you have taken biology 12 before, you've learned about this. So you end up with the negative region and the positive regions because of greedy electron. It has a high electronegativity, which leads to this unequal sharing. Another video listed, it's a short one, on the Moodle site. So now if we take a look at these ones and we take a look at their electronegativity, still using that reference sheet, if I were to rank these, I can predict which side of the molecule will end up kind of having the electrons more of the time. So if I rank these ones, they actually have the same value. So the nitrogen and chlorine, they actually bond equally. So that would not result in a dipole moment for that molecule. Nitrogen and phosphorus would give me this one that really wants to give, and this one really wants to get. And so that would be a negative and a positive region as it's going that way. The electron is going that way in this sharing. So we've got nitrogen and sulfur. And again, I'm just pulling those numbers so I can see which one is the bigger. That's the one that's going to attract the electron more of the time. And it seems like the textbook rewrites them sometimes to put one on the left and one on the right. I don't think it matters so much as you know which is the negative. Oops, sorry, I did that one backwards. Let me just fix that one up. Probably noticed as I was doing that. So the big one wins. So this one is 2.5. And again, sorry, big one wins. Big one's the greediest. Nitrogen, let's see if I can get this one right. I've got a 3.0 and a 2.5. There we go. Big one wins. The big one is the greedy numbers, the highest electronegativity. That seems like a good place to stop this. We'll come back and finish the chapter 12.